virtually. Thanks for the introduction. So as you heard, I recently finished my PhD in Edinburgh, where I wrote a thesis on program analysis for probabilistic programs. And in this talk, I will talk about some of this work. The way I like to start this talk is by taking a step back and thinking for a second about what's the goal of probabilistic programming. And I think the goal of probabilistic programming, at least in some sort of like perfect world where we can make it work, but the goal of probabilistic programming is to provide the tools to domain experts to completely focus on modeling and sort of not think about inference at all. So probabilistic programming should completely automate, make better this the inference side. Now, of course, oh, sorry, I'm having a problem with switching slides. Oh no, oh, there we go. Right, so the way I like thinking about it is on three axes. So we want a language to be general so that we can express any sort of model we like. We wanted to have fast, reliable inference that gives reasonable results and doesn't take forever to run. And we want it to be user-friendly, which includes this inference being automatic. Of course, in reality, things are not that easy. And because of the difficulties that we have with different inference algorithms, different probabilistic programming languages need to sort of make different decisions about on which axis to sacrifice. And here we have some examples. So in some cases, we have restrictions of the language, such as, recursion can only be bounded, or only discrete variables are allowed. In other cases, we sacrifice usability, in a sense, by making the language making inference less automatic, so that the user needs to do some work alone to write an inference algorithm. And then in other cases, when we have general models and automatic inference, we are forced to use general purpose inference algorithms, which are usually slow. So even though the dream is to have all three of these things, in reality, we're in a sad world where we need to pick at most 2 out of 3, or at least sacrifice in one axis or another. So the main question I looked at during my PhD was, can we improve probabilistic programming in one of those directions through program analysis? So can we take a probabilistic programming language that probably already exists and try to make it either more automatic or more general or faster, I guess. And I'm going to talk about one of the research areas we looked at, which is conditional independence by typing. This is published TOPLAS earlier this year, and it's joint work with my advisor, Sandy and Charles, and with Mathis Vakar. And this work is about STAN. To be precise, about slick STAN, which I'm gonna say a few more words about later. But basically, it starts from the following question. So inference in STAN uses the gradient, because inference in STAN is usually done with HMC, so it uses the gradient of a joint likelihood. However, because we need this gradient, we can't have discrete parameters, or at least we can't have them encoded explicitly in the language, because we can't differentiate with respect to discrete parameters. So so this is one of the restrictions, I guess, that STAN puts on its language in order to allow for efficient inference, right? We don't allow explicit discrete variables. However, there are workarounds this, and actually the Stan manual describes one such workaround, and this is to marginalize out the discrete parameters in the program. And the manual says how to do this manually by hand, but this research looks at it from the point of view of, can we automate it? Can we automate it with some sort of program analysis so that we don't have to do this? So basically, the whole idea is take Stan, or actually Slick Stan, with allowed discrete parameters explicitly in the language, and translate this to regular Stan, where they're marginalized out automatically. So again, I will use Stan and Slick Stan interchangeably in this talk, but really all the examples are written in Slick Stan, which is sort of a blockless version of Stan that uses information flow analysis to translate back to Stan. Okay, so now to see the problem with an example, consider the following model. This is a change point model where we say that there's some disasters happening at a particular rate, but this rate changes. So we have until year T, the rate is E in this case, so the early rate of disaster, and then after this point in time is at some other rate, L. And you can see this modeled here. So if we maybe, I don't know if you see my mouse.
Yes, we see it.
Okay, laser pointer, okay. So thank you. We see here that, so each data point is Y is the number of disasters that happened in year T. So if this year T is before D, the change point in time, then it's earlier rate, and otherwise it's late rate. And of course, D is an integer, right? So this is a discrete parameter. And we want to write this program as it is in our language instead of marginalizing it out by hand. And what do we want to happen? So firstly, this is what in Stan and Slick Stan, this is what this program means. It's essentially, it encodes the joint joint distribution between all the variables, including both parameters and data, which in this case is this. And what we can do is, like, we can literally, instead of looking at P of Y, E, L, and D, we can look at P, Y, E, L, where we marginalized out D. And this is how we write it in Slick Stan. Actually, here I've written it as not in log space for just for simplicity of the code, but actually in the actual language, this all will be plus equals rather than times equals, because it will be in log space. But the idea is we have, for each D, we calculate the log joint or the joint in this example, and then we sum over all of the different cases that they could have been. And that's it. That basically, so now this is the kind of program that could be written in Slick Stan or Stan, and we are almost done. The only thing that we need to do other than this is that we want to, if we need to, we want to resample back D. So we want to also get samples for D rather than just for E and L, which will be the case over here. So all of this looks very easy. It literally just looks like, oh, okay, take your program, put like a massive sum around the whole thing, sum out your discrete variable, and you're done, right? So firstly, why would we even care to automate this? Secondly, why would it be hard to automate? It doesn't, it looks so easy, right? Okay, but what happens if we have more than one discrete variables? So for example, if we have n discrete variables, that means that if we do it easy way that I just described, we would have to have n nested loops and nested for loops, which of course doesn't scale. So we can't really do that. But if the discrete variables are loosely dependent, so for example, one very common example is with a hidden Markov model. If they're loosely dependent, we can actually do that more efficiently because of exploiting conditional independencies in the model. And we can do that with only n two nested for loops rather than one big n nested for loop. And the idea of this research was to somehow find a way to exploit these conditional independencies so that we can do the marginalization efficiently. Here, well, I very quickly explained what variable elimination is, which I suppose is, it's not needed for this audience, but I'm just going to say it very quickly in case somebody's familiar. So variable elimination is a very simple inference algorithm for graphical models. When we have a graphical model and we want to marginalize out one of the variables in this model, we just look at the neighboring factors. We remove the variable, we remove the factors, we combine them in one big factor, and we put a sum over all the values of that variable. So this is basically how to take some big model that we want to marginalize variables from and do it efficiently, right? And this kind of tells us, okay, Z1 here is conditionally independent on Z3 given Z2, so we don't have to think about Z3 when we're doing the marginalization. And what we did in this research is to actually automate variable elimination through information flow analysis over here, and but automate it in the sense of rewriting the code inspired by variable elimination, so that at the end we actually use program slicing to reorganize the program, and now the program is still a program, right? We haven't even executed it, but it doesn't contain any discrete variables. Or discrete parameters rather. It did that in the sense as a compilation step. Right. So what do I mean by information flow analysis, which I mentioned several times? So information flow is essentially just the transfer of information between two variables. So here in those examples, we see that there is information flowing from X to Y in both cases, because here Y depends on X, and here again, even though it's not explicitly through deterministic assignment, but it's through an if statement, still Y depends on X through information flow. And information flow analysis is very much used in the security community, where we typically think of information flow as information flowing from public to secret. So we have in a system, we have some data points and or variables in our program, and we know some of these variables are public, some are secret, and we don't want any information from secret to flow to public. So we use information flow analysis there by associating a type level with every variable in the program, and this level is either public or secret, and we want to allow statements like this. So secret depends on public, but we want to disallow public to depend on secret. And And this is done with this lattice where information is set to flow from only up the lattice like this, so from public to secret. In our case, with SlickStan, originally there was, for those of you who are familiar, there was this, again, this lattice, but it was a bit different. It was with information flowing from data to model level to GenQuant level, or generated quantities level, but not vice versa. And in the case of this research with the conditional independence analysis, we have something a little bit different. So we again have levels. We have 3 levels, L1, L2, L3, but now we don't have a lattice. They don't form a lattice, but they form a semi-lattice. So information can flow from L1 to L2, and information can flow from L1 to L3, but it can't flow in the opposite direction, and also it can't flow between L2 and L3. So L2 and L3 are sort of like completely separated from each other via L1. And I hope this sort of sounds familiar. So I hope it sounds a little bit like conditional independence, because it's exactly that. The idea is that if we have, so looking at this graphical model over here, if we have some variables that are at level L2, because we know that this level L2 is completely separated from L3 given L1, this is like XL2 is conditionally independent on XL3 given XL1. So we can essentially eliminate these variables that are of level L2 without thinking about variables at level XL3, sorry, at level L3. So what this allows us to do is to take a program like this. So this is a version of a hidden Markov model like before, but just written in a bit more chaotically. So you can see that we have some sampling happening here, but we also have assignment of some of the parameters for the Bernoulli variables, and the statements that really are associated with, say, Z1 that we want to eliminate are scattered around. They're not at one place. But using information flow analysis, we can sort of detect which statements we should be looking at if we want to marginalize out Z1, and then slice the program and reorder them so that we put them all together and marginalize Z1. So this is what this elim does. It's just syntactic sugar for marginalization, essentially. Okay, so to recap all of this, what we want is we have some model with both discrete and continuous variables, and we want to sample both the discrete and continuous variables. But we want to do that efficiently. So what we do is we rewrite the program. So we get essentially 2 programs. One program allows us to sample only the continuous variables from the marginal of P of continuous variables given data. And then the other piece of program allows us to sample, given the continuous samples we got, allows us to sample discrete variables from the posterior discrete variables given continuous variables and data. And the last thing I wanted to talk about, oh, sorry, my mouse is going weird again. The last thing I wanted to mention is that even though this research describes one sort of factorization that we can do with type systems in probabilistic programming languages, my feeling is that there is a more general way of doing this, because essentially what we had with the original SlickStan paper, or after improving it a little bit, was a way to take essentially a program that gives us this joint between data and parameters, and factorize it based on what can be generated using ancestral sampling. So it gives us this factorization of P of B theta 1 times a P of theta 2 given D and theta 1. And the important thing about the factorization it gives us is that if we sample with any algorithm we want, so say HMC, we sample theta 1 from this, then we can just use ancestral sampling to sample theta 2. So all this is sort of like purely generative code. So basically the data doesn't depend at all on theta 2. And then this research gave us this different factorization, again with information flow analysis and type inference, which is a conditional independence factorization. So that's all I wanted to say for today, a bit early, which I guess people will be glad for. So I will take any questions that there might be.
Yeah, great. Thank you, Maria. As before, if you have any questions, just unmute yourself or write them into the chat if you like.
Well, I'm going to have lots of questions for everybody. I'll just jump in with a quick one since no one else is speaking. So could you do the same thing for continuous parameters? This sort of gets back to, I think, what Andrew Thomas was talking about earlier, and like detecting conjugacy and things like that. Like if you've got like a gamma Poisson, you might be able to sneak in a negative binomial or something.
Thank you so much for this question, Bob. This is a really good question. And yes, absolutely. So for the conditional, this sort of marginalization of discrete variables case was just an example of what we can do with the conditional independence analysis. It doesn't matter for the type system and the whole factorization of the program. It doesn't matter if the variables are continuous or discrete. So yes, we can do it with continuous variables.
Maybe if there are also other questions, since we are now in a bit of a delay, I can suggest that we shift our schedule 10 minutes late. So we now will have about 10 minutes or so of space remaining from the original break. But in that time, we can also take questions for the previous talk, or you can get a glass of water, anyone. So any further questions?
I have one more at least. So Maria, is there a way to detect the intractable cases? Like if I try to do like variable selection and I wind up not being able to marginalize out the discrete parameters? Or like, where do you draw that line? Because at least with 2 or 3 of them, you could do that, but with 100, you can't.
Right, so you mean, what if we have really densely connected model where we can do some sort of counting to see how many variables there would be and throw an error based on that. I don't know. I mean, I don't have a good answer, because unfortunately, if we have a densely connected model, then this sort of marginalization is going to be inefficient. What we could do, though, is if there is another way of doing the marginalization, like if we have some sort of module, for example, that can estimate it somehow, we could rewrite the program that way instead of with for loops. Because all of this is like we don't actually execute the for loops until we are ready with all of this, right? It's literally just rewriting the program.
Great, thanks.
Yeah, I got a. Oops, sorry. Was somebody else going? Okay. Could you go back to one of your slides with code on it with like the slick stand refactor? I think there was yeah, that one works.
This one?
Yeah, that one seems fine. Is there anything? I know. One of the things about Stan is like even like the sampling syntax is sort of like it's like a little bit of like a sleight of hand. It's just there aren't actually like priors and likelihoods or probabilistic things. It's more just like accumulate that target log density sort of thing. Are there any assumptions sort of in here like that are sort of taking advantage of like the sampling syntax or anything? I'm sort of trying to think more about like the mechanics of how we're going to like identify these conditional independencies and stuff. And since we have a couple minutes, maybe you could point to those things.
So that's a good question. For the conditional independence analysis, the sampling doesn't really, no, it doesn't. We don't care about the sampling. We can write all of this with just target plus equals.
Okay.
But for the other one, for the for this one, where if we want to separate what we can sample with ancestral sampling from what we have to sample with something else, for that it is important because we need to have a generative way of so we need to have this sampling statement.
And since you sorry, actually, what is ancestral state or ancestral sampling? What is that?
All right.
Sorry.
So if you don't have any data, if you say you have X coming from normal 0, 1 and Y coming from a normal X1, if you don't have any data, you can literally just sample X from 0, 1 and then sample, given that sample that you just got.
Okay. Okay.
Yeah. So this is ancestral sampling.
Okay, that makes sense.
Sampling. Yeah.
Oh, okay. Okay, cool. Thank you. Thank you. That's good. Other person, you had a question?
Right, Maria, thanks for the talk. Very nice. I got a question which is about potential limitation of this static analysis. Am I right in saying that these analyses are assuming the graphic structure underlying the model is not changing during inference?
Sorry, can you repeat the last bit of the question? I'm assuming?
I'm saying, are we assuming the graphical structure, the conditional independent structure of the model doesn't change during inference?
Yes. So it is, I mean, like, not unlike other STEM programs, I guess. We need to have a fixed parameter space, so it doesn't change. And another assumption, obviously, as we've already pointed out, is that the discrete variables in the model will be loosely connected. So it will be a sparse, at least when it comes to the discrete parameters, it will be sparse, because otherwise it will be very inefficient. And what else are we assuming? I can't think of the top of my head, but yeah, there are a few assumptions, yes.
Cool. Thanks a lot.
No problem.
Then maybe something from me. So I guess with this principle of propagating information flow through the program, you can also do things that are really not that much related to the independent structure, like discovering the parts that change and not change if you have such a program that is not like Stan, or checking semantic invariance between discrete, say, you must not use a negative value in a certain distribution and that. Have you done anything in that direction, trying to generalize this as a principle of analyzing PPLs?
Yeah, thanks for this question. So that's why I put this this last slide, because I really do think there is something more general. I have not, so this is kind of towards the end of my PhD, I started thinking about this, but because I moved into industry, I haven't really had the chance to explore that. But my gut my gut feeling is that yes, we can somehow generalize this so that we can factorize a program in all sorts of different ways, which, you know, ties a little bit the whole thing to ideas such as programmable inference, maybe when we want to write our own inference algorithm, but have the system help us do it, right? So by saying, for example, oh, you have this chunk of program and this chunk of program, we generated these chunks of program automatically for you. Now you can write one inference algorithm for that and one for that based on what the properties are or something of the sort. So yeah, that's kind of my dream in my head, at least.
Thank you. Any other questions?
I think Pavan raised his hand during Chris' talk. Pavan, do you have any questions?
Hey, yeah, if Chris is still around, I can ask.
Yeah, I'm here.
So I had two questions. One was the sort of state of modeling toolkit, like in which instances it's better to use modeling toolkit, or if there are some cases where it's still better to write it in differential equations directly. And the second is which sort of pipeline you prefer when you're working in industry, say in Puma's AI. Is there a particular modeling pipeline that you have that goes between differential equations and modeling toolkit and Turing?
Yeah, so two very good questions. Yeah, so when we so let me answer the second one first because it's a bit simpler. If you actually look at diffie-cube Bayes, right? So one of the difficulties with Turing or any other domain-specific language is that it's hard to generate code that will target a domain-specific language, right? Because, you know, a macro or something like that, it wants to know what your actual variables are named. But if you are working in a space where, you know, you're generating code, then you don't necessarily have names for everything. Right. So I think that the best version of this that's public that you can kind of use is if you look at this file in diffie-cube Bayes, right? It's a wrapper. So we built this wrapper for Bayesian inference algorithms to make it simple. So that way you can basically not use the PPL, but use the PPL for people who are differential equations, but not PPL people. And so, you know, it can do things like take a ODE problem, automatically convert it to Stan, and then run it in Stan, right? And it does this with Turing. And let me just kind of show this really quickly. The way that it does it is it uses interpolation into the macro with fixed names. And so, yeah, this is, and we actually had a version 2 as well. If you look at earlier versions of this code, there's ways to go underneath the macro. Let me see if it's far enough. Yeah, there's ways to go underneath the macro and just directly call a lot of the internals. So we do a lot of these bits. So we're still hitting the Turing front end because we want a lot of the features of the Turing front end instead of hitting something like the sampler directly. But there are little tricks that we have to do when doing that. And we've worked over the years with the Turing developers, especially with Mohammed and such, so that way we can actually have the right things to be able to hit here. Definitely Turing was in its first versions was not set up to be able to do this well, and we had to, you know, to have our asks and, you know, a bunch of back and forth to be able to get to something that we can target there. But yeah, and that's how come we're able to now in version 3, you know, we're able to actually use the macro in a specific way. But, you know, it's still in a very specific way, and we can discuss more on that later. So yeah, so when we're doing this inside of Puma's AI and everything, you know, it's very different from like your standard PPL usage. You know, it's not like you get your named versions or anything. So we have hard-coded names in the code that we're generating, and then we go and fix the names in post, essentially, right? So we don't take the standard output that Turing's going to give. We then have to re-nudge it with the names from our own DSL into that. So yeah, so then the other thing was the other question was what part again?
Just sort of the state of modeling toolkit and the use cases for when one should use modeling toolkit or writing your own stuff in differential equations.
Yeah, okay, so I would say that most people, if you're doing a differential algebraic equation, you almost certainly want to use modeling toolkit because there's just so many things that can happen with differential algebraic equations. There's so much support for eliminating equations and such that you want to use it, not just for the improvement that you get from cutting down equations, but also for the stability and accuracy. All those things with DAE index reduction. There's also a lot of details beyond that I didn't go into. So when you do index reduce, sometimes you want to include dummy derivatives because they can stabilize the equations and partial state selection. We'll have some nice talks that come out about this soon. You can look up some of the older literature on this, though I don't think that it really makes it fairly explicit. So we're going to be trying to show people like, hey, this is an equation that will fail without dummy derivative techniques and such. But so if you're doing a differential algebraic equation system, these days, I know that modeling toolkit's not ready for everything, but differential algebraic equation systems, it's so hard to know which ones are truly solvable by solvers that these days I just point everyone to modeling toolkit because they don't want to have to handle their special snowflake, right? Like it's like there's a program analysis that can tell you whether it's a hard one to solve. So please run the program analysis, right? But there are some issues with the current form. So the kinds of algorithms that it has to do these analyses naturally has to scalarize things, which means that your loops fall down. There's two consequences of that. The one consequence is that if you have a loop of 1 million things, then you have a 1 million equations long code, which takes a while to compile. The other thing is that when you unroll loops, you no longer have the loop vectorization intrinsics of LLVM apply, right? So there's in LLVM, there's two different ways that it can apply SIMD. It can either do loop vectorization intrinsics, or it can do what's known as SLP vectorization. SLP vectorization has to check all combinations of vectors though, so it's really slow. It's actually disabled by default in a lot of optimizers for that reason, especially when you have million line code. And so you get worse SIMD performance. And so you can actually decrease your runtime for if you have something that's just a loop, like a partial differential equation, it can reduce your runtime because it's relying on SLP instead of loop vectorization. Now that's going to be changing. We're building new symbolic IRs that can allow different kinds of analyses and keep loops intact, right? But this is one of those things where right now there's a trade-off. So there are some nice packages like method of lions.jl for doing PDE discretizations via modeling toolkit, but their compile times and runtime performance don't match what you get by hand right now. And that'll probably be true for another year or two.
Okay, cool. Thanks.
Now that we're at it, I actually have another question for Chris. So I have no background whatsoever in ODEs, but I was wondering, it looks like you can optimize in these kinds of programs for two kinds of things. So you're trying to find the best solver for your model, and you're trying to find the best sampling algorithm for the probabilistic program. Is there a sort of interaction between that where the optimum thing is not just find the best solver and find the best sampler?
Yeah, I'll say that I'm not sure. That's actually what's starting to push me more towards PPLs, because I mean, like even the sampler is an ODE solver in some sense, right? It's a symplectic integrator. So we got a back end into Turing where we can actually use the different symplectic integration algorithms as the sampler inside with nuts and such. And I mean, this is something where I'm looking for a graduate student who'd be interested in looking at. My guess is actually that some of the Ruth methods, so Ruth 4.3 with the optimized tableaus, may actually be a bit more efficient than some of the symplectic integrators that are used today. But I think that's something that needs to be looked into in detail to be able to really make a solid statement about. And then I think that one of the things that's really interesting too is that you have a relationship between gradient accuracy and sampling performance, right? So if you have inaccurate gradients, then you might want to use different samplers. And so, if you use an ODE solver that has a higher order and, to a higher tolerance or to a lower tolerance, right? You might actually want to use a different sampler. So a different order method for your symplectic integrator, right? So you might want to use a lower order symplectic integrator with smaller steps. If you're solving the ODE with higher tolerances, but then you might be able to use a higher order integrator with larger time steps in parameter space if you solve the ODE more exactly and get more exact gradients. that's a hypothesis right now. I'll say that this is something that I really want to look into. But if any graduate students find that question interesting, then definitely, I think that there's a lot to do in this area.